Hi y'all, welcome to week 11 of BUSS1020. So in this week we continue talking about simple linear regression. So it is part 2 of simple linear regression that we carry on from last week. After week 11 we have week 12, which is a multiple linear regression. Um, and then after that we're done with BUSS1020's content. So without further ado, let's get into the content. So firstly, looking at our modules, we have a week 11, which talks about part 2 of simple linear regression, residual analysis, text for linear relationship. So there are a few rules, linearity, equivariance, normality. For examples, are some examples of um, uh, characteristics that are needed in order for linear relationships to exist. Estimating means of individual values, autocorrelation, pitfalls in regression, and reviews and workshop. Again, as always, we're going to be using the workshop material in Excel and in Word to talk about some examples. Okay, so firstly, simple linear regression part 2. We first talked about some assumptions of linear regression, some assumptions that must hold true in order for linear regression to take place. The first thing is we assume linearity. So we assume the relationship between x and y is linear. Now, once again, the reason we do this is if we see data such as this, could we see that we can obviously see that this is quadratic, right? So because it is quadratic, we reject the assumption of linearity. Another thing we could do is if the data points are like this, then we also have to reject the assumption of linearity. This seems like something that is like an exponential sort of function. So the assumption of linearity is really quite important in regression analysis. Second thing is independence of errors. So error values are systematically independent from each other. Another thing is normality. Error values are normally distributed for each given value. This assumption is only needed if the sample size is less than 30. Also equivariance. So the distribution of errors at different values of x has an equal variance. Now, what we mean by equivariance is homoscedasticity. Homoscedasticity. As we can see, data right here does not have equal variance. The variance between variables increases as x increases. Whereas on the other side, the variance between these data points towards the best fit line is relatively equal across as x increases or decreases. Therefore, the assumption of homoscedasticity holds true, and therefore equivariance is assumed, and therefore we could use linear regression. So that is one of the assumptions. Now another one here right here is residual analysis for independence. So we know linearity is quite a easy assumption. We know normality is quite an easy assumption. We've talked about equivariance, and now here we talked about the independence of errors. So right here we can see that these are not independent. We can see some sort of trend. Okay, and the Durbin-Watson statistic that we're going to be talking about later, it could be used to predict whether or not there is a trend, whether or not residuals are independent or dependent on previous data points. Okay, so hypothesis test for linear relationships. So once again, we have hypothesis testing in linear relationships. This is the linear relationship where if there is a linear relationship between x and y, then then we reject, then we accept the no hypothesis. Whereas if there isn't, then we reject it. All right. We can show that beta 1, so if there is a linear relationship between x and y, then we should reject the slope equals 0, aka reject the no hypothesis when beta 1 is equal to 0. We reject the correlation coefficient as 0, aka also known as we reject the beta 1 equal to 0. If we can show that beta 1 and r are far enough from 0, then it is statistically likely true that the true values were 0. Then we could conclude that there is a linear relationship to a particular level of confidence. Alright, let us look at an example right now. Okay. Looking at this example, we are plotting square feet of a house on the x variable to y variable. So y variable is the house price. Now, the independent variable is the square feet, and the dependent variable is the price in thousands of dollars. Now, what we could do is we could use the, first of all, we need to have to know an alternative hypothesis to see whether or not there's a linear relationship between these two variables. Furthermore, we could use the data analytics. Freak the British pronunciation. I'm gonna use the American data analytics to determine these variables. So we could determine the t stat. We could determine the B1 and B2. So we could see that all right. So inferences about slope using a t-estimate, t-test example, into critical values. So the decision is to reject H naught because once again, the t-stat lies within the rejection region, whereas based on the 5% level of significance, we could see that the 5% level of significance will have t at both sides at negative 2.3 and positive 2.3. However, at t-stat, based on the calculation from the data analytics toolpack, puts our t-test variable at 3.32, therefore there is in the rejection region. So there is significant evidence that square footage significantly affects the house price at a 5% significance level. All right. Alternatively, we can also look at the p-value. So once again, when we talk about, we always have the saying, when p-value is small, H naught must go, right? So when p-value looks low, so right here p-value is, what is the p-value? P-value is very low, okay? P-value is less than 0.5, so we reject H naught since p-value is less than the alpha of 0.5, of 0.05. Okay, next we have estimating mean and individual values. So the goal here is to estimate. Okay, the goal right here is from intervals around y to express uncertainty about the values of x given x1 or xi. So estimating mean values and predicting individual values. To form intervals around y to express uncertainty about the values of y for a given xi. Okay. We have the confidence interval formulas as well. Once again, confidence intervals always have three components: the point estimator, the critical value, and the standard error. So it is always the point estimator plus or minus, because there are two sides for the confidence interval, the critical value multiplied by the standard error. So that's the standard formula for all confidence intervals. All right. Lastly, we talked about the Durbin-Watson statistics. So previously, we talked about autocorrelation and how autocorrelation or the non-existence or the independence of data from one another is one of the important assumptions that we have in linear regression. So in order for linear regression's assumptions to hold true, there must not be autocorrelation. Variables and assumptions must be independent. So as we can see, the left chart right here, we can see some sort of relationship, some sort of a trend that is happening. However, on the right, we can see independence of residuals. Okay, how do we test whether or not there are independence of residuals? This is where autocorrelation tests in the form of the Durbin-Watson statistics will come into play. So autocorrelation is the correlation of errors or residual over time, where data is related to itself. It violates the regression assumption if there is autocorrelation. So we can use the Durbin-Watson statistic to measure whether or not there is autocorrelation. So used when data is collected over time to detect autocorrelation if present, if autocorrelation is present. If autocorrelation exists, if residuals in one time period are related to residuals in another time period. So here's the formula for autocorrelation. Using Excel to calculate the Durbin-Watson statistic. And lastly, the 7 steps to avoid potential pitfalls. All right, let's look at the Excel. All right. So a known alternative hypothesis, once again, is equal to 0, not equal to 0. If there is a linear relationship, then we reject H naught. Being equal to 0, SSX, XB1, T stat, critical value, P value. Once again, P value is small, then H naught must go, so we reject the P value. And then we can also calculate, so for testing correlation coefficients. Oh my gosh, let me close the windows real fast. These ambulances do be tripping. All right. Sorry about that. So we can see R value, we can see a standard error. These are used to calculate the confidence interval later. T stat, critical value, P value, and then here we can see the confidence interval. All right. Okay, let's quickly also look at the formula list. Population covariance, sample covariance, population coefficient. Okay. Alright, so I think that pretty much sums up week 11 of BUSS1020. So we really talked about some assumptions for linear regression, how to test whether or not these assumptions for linear regressions hold true, hypothesis testing, we revisited hypothesis testing for linear regression, and also introduction to a Dove and Watson test statistic to test or not whether or not there is autocorrelation between data points, so that we could see whether or not the hypothesis or the assumptions for regression analysis holds true. So I hope you took something away from this video. Without further ado, I hope to see you guys next time. Well, we will be wrapping up this module or this entire course with multiple linear regression, and then we'll have some review videos going through the entirety of the content. Exams are in 14 days, so at the time of the recording, so certainly on the purviews are certainly coming up soon, so expect some review videos, expect some videos that goes through the entirety of the content. I know for some subjects like BUSS1020, I'm probably going to read the entirety of the textbook on camera probably. Yeah, so some exciting things to look forward to. Without further ado, take care and goodbye.